Consecutive, let's talk ordered. Let's go an ordered list that follows a pattern. Usually in math, there is actually a whole field of random variables, but we're not going to deal with that. We're going to follow a pattern. Now it's important that you think commas, because when I say is a sequence the same as series, the answer is a big fat no. A series is, say, is exactly the sum of a sequence. A series is the sum of a sequence. So, for example, if the sequence is 1, 2, 3, 4, then the series that corresponds to it would be 1 plus 2 plus 3 plus 4. Now, a sequence in a series can be finite, but in calculus we especially focus on the infinite, right? That's no surprise, I'm sure. Notations. It is common, almost universal, but not quite, that you use n to represent the number of a term in the pattern, in the sequence. Yeah, I'm not saying it is the term. I'm saying it's the number of the term. So, for example, in this case, 4 is actually, that's a terrible example. 4 is the fourth term. That's not clear at all. Say I gave you this, 2, 4, 6, 8. And if I said, what's the fourth term, you'd say it is 8. That fourth term, that's the n. What number of term? Okay? A sub n represents the nth term. So in this problem here, what is a sub 3? 6. Okay, the third term is 6. You with me? Okay, easy enough. And typically starts at 1, but it doesn't have to. You could start at any place you want as long as you define it, or unless the person said start at n equals 1, asking the question, right? Now, we have rules for sequences, just like we have rules for functions. But there is a little bit of difference. For example, when I say f of x is the square root of x, it would be like saying the nth term is the square root of n. In both cases, I could use that operation in either a function-y way or a sequence-y way to generate terms. This is called the general term. The term or the rule that could tell you any term you want. If I ask for the 7th term, the general term could be used to find it. The 7th term would be, assuming it started at 1, root 7. Okay? Now, they're a little different, however, in the nature of the numbers. Is it okay to work with x equal 0.3? Can I say, hey, square root of 0.3, is that doable? Sure, no problem. How about over here? Is it okay to say, hey, n equals 0.3? In other words, give me the 0.3th term in the sequence. No, that's dumb. There is no such thing as the 0.3th term in the list. Okay? No. N is whole only. There is no 0.3th term. There's the first term, the second term, the third term, and so on. Whole numbers only. You can, I suppose, once in a while go in integers. I guess you could say start at -1. That's rare, and it's weird. All right. Bounded above and below. Let's go with that. A sequence is bounded above if, I'll get you the formal part in a second, but what do you reckon that means? If it's bounded above, then what? Okay, geometric, that's true. Geometric would only happen if the common ratio is less than 1. It's good that people remember. Generally speaking, a sequence is bounded above if... Talk some calculus to me, people.
Asymptote.
All right, it approaches a horizontal asymptote, or it has an upper bound. What about this? Does it have to approach a horizontal asymptote? Is that bounded above?
Yeah.
It is. Okay, so it's not necessarily going to approach an asymptote, nor does it even have to approach a limit. What does have to happen is it's bounded above if there is some L, finite L, I should say, some finite number L, such that all terms, which I'm going to say A sub n, all terms, any term, is less than or equal to that number. What do you reckon that L stands for? Upper limit. Yes. Okay. If there is some finite number L such that all terms are less than that number. Bounded below then would be if there is some finite L such that all terms are greater than that number. That's the bottom floor, so all terms would be above that. If it was a lower bound, then it's less than all the terms in the sequence. So generally speaking then, a sequence is bounded if it is bounded both above and below. Give me a function that would be bounded above and below. Cosine and sine, bounded above and below. Okay, good deal. Monotonic. Do you remember what I've said that a couple times in this year, but I don't know if you remember. What does monotonic mean? Okay, so you stepped it out. And one, you definitely know what mono means, but what does the tonic mean? And the answer is big fat. No. It's a mix with liquor. Everybody knows that's what you mix liquor with. So, anywho, no. It means one side, really, and that's a reference to the derivative, actually. If the derivative has only one side, then the function is strictly increasing or decreasing. The pattern, the sequence either strictly increases or strictly decreases. If a sequence is bounded and monotonic, it must blank. Now, consider this. If I had terms that were bounded, so there was an upper and a lower limit, but they were only, say, increasing, then it must approach a number, as opposed to the sine that is bounded but not monotonic. It doesn't have a limit that it approaches, right? But if a function is bounded and monotonic, it must approach a number or get closer and closer to a number, which is to say it must converge. Now we'll get some vocabulary in there. I might have my slides in the wrong order, so would you please tell me, is this the next slide or the next part of your notes?
Yes.
Oh, super. Okay, so we'll come back to converge in a second, as you can see, but let's start with general terms. Now, the general term is really like the rule that makes the terms, all right? It can involve square roots or adding, multiplying, all the different things we've talked about for years. Okay? Now, we're also going to graph this, so let's do one or two together. So I'm giving you a general term, and you can assume, unless otherwise told, that n starts at 1. Okay, the first term. If the first term is 1, then what happens when I put 1 into the rule? The first term is when n equals 1 goes in, what comes out? -2. Then it goes up by 1 each time, the first term, the second term. So the second term is when n equals 2 into the rule, +4. When n equals 3, -6. And when n equals 4, 8. Now if I were to graph these, the number of the term, n, is on the x-axis, and the term itself, or the outcome, after putting that into the rule, is the dependent variable, the y-axis. In order to get all these on, I need to at least get to about 8. So the don't make your vertical scale too big. In terms of horizontal scale, we only have 4. So, when I say when n is 1, the term was -2, that means when n is 1, the term is -2. I put a point there. When n was 2, the outcome, or the second term, was +4. When n was 3, the outcome was -6. And when n was 4, +8. You want desperately to join them, don't you? And yet you will not. Why not? It's not a function. To put a point here is to say there is such thing as the halfth term or the 0.23th term. There is no 0.2th term. Okay? So you shall not join. They are dots. Get over it. All right? Yeah, what the heck? Obviously, then this function, this is not monotonic too. Good job. But I was thinking contiguous or differential. But here we go. Try the next 3. Try the next 3 on your own. Find the first 4 terms in the sequence. Graph the pattern. Call it good. Graphing tells you if it converges or diverges.
Even though it's not a
Oh, it's still focused. Don't be a hater on the sequences. You deserve a graph. How do Okay. The second one, I thought I was being so clever. Unfortunately, I remembered wrong. So what is the sequence? Okay, so can you imagine what I intended? All right, well, it would be cool as if it was cosine pi. Then what would it be? Cosine of pi is? Cosine of 2 pi is? Wait. Cosine of pi is? Cosine of 2 pi is? Cosine of 3 pi is?
So it just.
So it goes back and forth. So it's an alternating negative pattern. It's kind of cool. Okay, but that is not very cool because I use sine. So there you go. All right. Is this bounded? No. Is this bounded? Yes. Okay, what are these terms? What's the millionth term? 1 million over 1,000,001, which is doggone close to 1. 1 is half. Oh, I was thinking this one. Sorry, I was jumping ahead of myself. 1 2/3, 3/4, 4/5. Okay, is that bounded? You say yes. Is there a number that is less than all the terms? Can you give me a number that's less than all the terms? 0. Sure, 0. Or 1/2. Less than or equal to. Okay, so is it bounded below? Yes. Is it bounded above? Yes. So is it bounded? It is absolutely bounded. Okay. What are the terms here? -1, 1/2. Okay. So 1, -1, -1, 1/2, -1/3, -1/4. Is this bounded? Is there a number that is less than all other numbers? Yes, absolutely. -1, for example. Is it bounded above? Yes. Yes. So is it bounded? Yes. Yes. Okay. All right. Now then, let's talk a huge part of the vocabulary of series and sequences. Which of these approaches a limit as n goes to infinity? Does this approach, do the terms approach a limit as n goes to infinity? They do not. How about this? Yeah, can you tell me what the 100 millionth term will even be? Yeah, so do they approach a limit? Yes. Okay. What about this? Do these approach a limit?
Yes.
Yes. What is it? 1. Do these approach a limit?
Yes.
Yeah, what is it?
0.
0. So yes, those all approach a limit. If a sequence approaches a limit, now when I say approaches a limit, we don't really talk infinite behavior on the end behavior on both sides, yeah? Sequences, you don't say what happens is you go to the -1 millionth term. You don't do that. You go to positive only. So when I say does it converge, I'm always saying as you go to the millionth term, do the terms approach a number, a finite number? If they do, then you say the sequence converges. If they don't, then you say the sequence diverges. Now then, please pay close attention to the definition of diverging. Diverging does not mean the limit of the terms is infinity. What other case would be diverging, but the terms don't go to infinity?
And you're saying negative and cosine.
Yeah. Did these terms approach a finite number? No, they don't. Okay, and yet do the terms to go to infinity? No. Okay, so diverge does not mean terms go to infinity. Diverge means fails to converge, does not converge, does not approach one finite number. So oscillation is possible as another counterpoint to convergence. All right. That said, then, when I ask for you to tell me if a function converges or diverges, in the book, I wrote it kind of like the book does. It'll say, find if the sequence converges and diverges. You shall not say, yep, with no justification. It is implied that justification is required. The justification, as you might imagine, is satisfying the definition of converging or showing that it doesn't satisfy the definition. In other words, to show there is a limit to the terms. So I'll show you what I would like to see. To answer this question, does this sequence converge? I should see a limit statement. As the terms go to infinity, as the number of terms goes to infinity, or as I approach the millionth, billionth, trillionth term, the terms approach. The terms get bigger and bigger. Now, is there a finite limit to the terms? Therefore, it doesn't converge, so it must diverge. Okay? So the justification is taking the limit of the general term and saying what do the terms go to, and then saying converge or diverge based on that evidence. Try the other three, please. Excuse me. Okay. The hospital? Really? Angie, it says you're a basketball leader. You don't look like it.
Yeah. We leave it work there.
You don't want to miss the class.
No.
Exactly. All right, then. Are you ready? First one. Now, please keep in mind that although I'm sure your limit skills are superior, you can always generate a few terms if you wanted to just kind of get a flavor for the problem. What are the terms of this? We talked about it before. -1, 1, -1, and so on. So that right there is staring me in the face telling me that's not going to happen. But to show the work, I'm going to say if I take the limit of those, what is the limit? The limit is a number that the function does not exist. Remember, there are two reasons a limit doesn't exist: oscillation and okay. So this is Danny. If you want to say oscillation, I think that would be good math to say so. But you do not have to answer the question still. I didn't answer the question. It diverges. Okay? There is no finite limit, so it diverges. All right, what is the limit of the terms here? Oops. And therefore we conclude converges. There is a finite limit to the terms. My teacher actually made me write that full sentence out every time. There is a finite limit to the terms. I am fine with making the inference for you that 0 is a finite number. Okay?
You think that is like 0? I had second 0.
0, the limit is finite. How about this? This one requires a little bit of more work. As you might imagine, when we're dealing with infinite, there are going to be cases where L'Hopital comes up. And so this surely was L'Hopital, not hospital. And this, yet again, I still had one student in the last class get caught in ye old infinite loop of L'Hopital. She did something like this and said, well, oh, now that's 0 over 0. So I take some more derivatives. And what happens is you just keep taking derivatives. It descends forever into the depths of L'Hopitalness, right? So what should you do? Simplify. For Pete's sake, you simplify before you proceed. When you simplify, you get 2 over root n, which does approach a limit of 0, which implies that it converges. Now these two, that's a pretty important relationship in Calc 2, how natural log relates to root of n. I can bound log by root of n because root n is bigger. We'll talk about that when we get to P series, but that's a good relationship. Any questions so far? Cool. Okay. Last but not least, this is so interesting. This could be a psychology paper here someday. Some people it's like they're made. They just see it beautifully with no instruction. And some people, even with the best instruction, they just have no idea where I'm coming from, or where whoever gives good instruction comes from. At any rate, it's the idea of writing a pattern. This, first of all, change this. If you're going to plow ahead because you're good at these, change that to $75. Okay. Now, the idea is that instead of being given the general term and you write some terms, here you're getting some terms and you write the general term with a rule. Would you please give these a go? And I'm going to stop you after 1 or 2 to make sure that you understand the biggest idea of this at all. Try 1 or 2. Do you understand what you're doing?
Oh, you're writing this.
You're trying to write, the pattern for this is the general term. The nth term is this. I can find the nth term by this rule. Okay? These notes we'll talk about in a second. 1, 3, 5, oh yeah, 57, well, that's the second typo. Sorry, yeah, that would be rough. 50, no, it's 5, comma 7. Sorry.
Okay, now maybe I should put the first word. There's only one.
Would you also just please put in huge capital letters the most important 3 words to these problems? Check your rule. Okay, there are lots of different rules I could write. I could write at least 3 different rules for many of these. And that's fine, they don't have to agree, but you should always check your rule. You should never miss these unless you just run out of time. You should know if your rule works. Get you off on the right track first. Quick check. I had a really go-getter student say, oh, I know these, n plus 2. Okay, now what rule did he break? He broke the most important rule, which is to check your rule. When n equals 1, what do you get? 3, so that's a no. When n equals 2, what do you get? 4, so that's also a no. When n equals 3, so this is just wrong on so many levels. It's not even close. It doesn't even make one of those terms. Not even close, okay?
It makes it 30.
Does it? Oh, so it does. Okay, so sometimes even a broken clock, like twice a day, right? Less fastidious. Oh, actually, no.
That's the same thing.
Yeah, same thing. Okay, all right. Okay, less doesn't say anything. What's the rule here? What's a rule? 2n minus 1. The nth term is 2n minus 1. Does that check for n equal 1? Now notice I told you to start at n equal 1. I know technically you could, if I didn't say that, you could have maybe said, I'm starting at 0 and that's fine. But I'm telling you to start at 1. Does it work for 1? Yeah, 2 times 1 minus 1 is 1. Does it work for 3? Well, 2 times 2 minus 1 would be 3, so forth. Okay? All right. We work together. I'll give you some help with pointers on the right side.
Yeah. Darn it. Wait, what? Oh, I got the first one.
She's wrong.
That's so mean.
How you doing, people?
I was agreeing with Mr. Reagan.
Oh, wait, that one on the last two combined.
Oh, I want to write that down.
Okay, so I went to the Fibonacci convention this summer, and it was better than the last two combined.
It's a hoot. That's a good one. Okay. Are you at an impasse, or should we keep giving you some more time?
I am. I'm sure everyone else is fine. I'm pretty proud of myself. I got 3, which is to like 5 minutes. Oh, 3 and 2 and 3 and push it. That's not very good. No, that doesn't work. No, it doesn't. I know that's 3
And keep in mind there are lots of different solutions that could both work.
How did you figure that out?
What he does. You're good. You'll be funny.
Oh, you too.
You'll have some strategies, and you'll think these are super easy pretty soon. You will have strategies. You will. There's so much math going on, it's flying all around you, and you don't even know it. Just have to learn it. Should we go so we have a little bit of time for homework? Okay. So this, I don't know if you recognize that, but that is odd numbers, yes? What's a way to make odd numbers? Should you see them in a pattern? 2n minus 1. You could also use 2n plus 1, depending on the case. Actually, 2n plus any odd number would get you another odd number. How do you make even? 2n. Now, you're always assuming that n's are whole numbers. If n are whole numbers, then when you put them into 2n, you'll get an even out, or an odd out, as the case may be. Alternating negative, I know I talked earlier about this cosine pi n one. That's actually just kind of a funky, fun one, but it's not the most common. The most common way of getting alternating negative is negative 1 to the n. Do those parentheses matter? Yeah, without them, what is it? Always negative. Yeah, so that's not so interesting. It's the parentheses matter. Arithmetic. What does that mean? If a sequence is arithmetic, there is a common difference. You could think of it as an adding pattern, always adding the same number. And if I always add the same number, add 2, add 2, add 2, add 2, what kind of math pattern is it? Linear. Arithmetic is linear. Geometric is a common factor. Students always want to say factor, but it's a common ratio or factor, I suppose. Yeah, that's why it's called R, not F. Okay, it's a common ratio or factor. It's multiplying by the same number. What notation do we have for that? If I multiply by 3 over and over and over again, what notation do I have to do that? 3 times itself 100 times. 3 to the 100, also known as exponential. Geometric growth is exponential growth. It grows really super duper fast. All right. Looking at differences, use derivative knowledge. I'll explain that in a minute. Let's go over here. There are actually, I see that second one, I see 2 patterns at work. What are they? There's 2 things going on there. There's an alternating negative, which I am referring to the cosine thing, and then there's a 2. Yeah. Okay, so how do I make an alternating negative? Well, I could do the cosine thing, or I could do that. Either one is fine, cosine of pi n, or that. But I also need to make it 2. Now, I told you, and I'll tell you again and again and again, check your work. Does that work for an equal 1? No, that would be negative 2. That would be a starting negative 2. Do I get a starting negative? No, I want a positive 2. So what? A couple things I could do. What can I do? I could call it negative 2. That would work. What's another thing I could do? I could bump it up something like that. Now, there's lots of possibilities. All right. What do you see going on here? Common factor or difference? Difference. Common difference. You're always adding 6. Okay? So, give me a rule.
3 times 2n plus 1.
3 times the quantity 2n plus 1?
Yes.
Okay. Does that check? When n equals 1, I get 9, and it seems like it continues. What if somebody else had 6n plus 3? Isn't that equivalent if I just distribute it out? So there's lots of different rules. Okay? Either one is fine. You could definitely jump to this. Don't overthink it, man. I mean, it's writing the equation of a line. What's the slope, but what's the change each time? 6, and then you just have to figure out, okay, how do I start it until make it work, right? So 6n, and then figure out a starting point. What about this? What's going on here? Is there a common adding difference? No, that's out. Is there a common factor? Am I multiplying by? No. No. So what is going on there?
Sequential squared.
Yeah, it's squares. They're squares. 2 squared, 3 squared, and so on. But unfortunately, I can't just say n squared because that doesn't check. So what do? N plus 1 squared. I need the base to be a little bigger to start with, so I'll add 1 to the base. So it starts at 2. Okay? Yeah, smart people tend to overthink stuff a little bit. Luckily, I don't have that problem. So, 75. Look at 75. Or the next one, which is much easier once that's 75, because the last class, they worked really hard to try and find that. They got nothing before I changed it. So, what's going on here? Times negative 5. If it's times negative 5, so let's be clear. This, you could say, is 3 times negative 5 no times. This is like 3 times negative 5 one time. This is like that times another negative 5, so you could say that times another negative 5 would be 2 times. So generally, we could say this is 3 times negative 5 n, or n minus 1. Yeah, which one? Is it n? It is n minus 1 that works. Okay? Okay, now, how many patterns at work here? 3. There are 3 patterns there. What are they? Alternating negative, that's one. Numerator's different, they're different. The numerator and denominator are doing different things. They're not following the same pattern. So there are 3 patterns there. Negative 1 to the n or n plus 1? Would n work? N would start at a negative. Do you agree that would not work? So it needs to be n plus 1. You could also do n minus 1. Okay? What about the numerator? What's going on in the numerator? 5, 7, 9 odds or arithmetic. So 2, 5 plus 3 plus 2n. 2n plus 3 works. Because if it's going up by 2. First of all, let's agree on the 2. Do you agree that 2 makes sense because it's going up by 2 each time? Okay, the 3 is there because it's kind of got to be there to start us off right. Okay. What about the bottom? 2 to the n, it's surely 2 to powers, but n doesn't work. It needs to start off at 1 more. Could I also go 2 to the n and bring in another 2? Does that work? Yeah, aren't those the same? Yeah. Okay. This is a humdinger. This is one of the most famous sequences of all time. It's right up there with the sequence you learn as a 1-year-old, which is 1, 2, 3, 4, 5, 6. Yeah. If you don't learn this as a 1-year-old, what is this called? Yeah, that's the Fibonacci sequence. Some of you probably studied this. Quentin, you probably have studied this. Yeah? Is it? It's fascinating. And you can take, in college, that's one of the coolest things about college is they get super specific. You'll get some professor that Fibonacci is his passion. I mean, he's dedicated his whole life to Fibonacci, and he could talk for a month, a semester, about Fibonacci. And he'll point out there at the tree. This I actually have this class. He said, you see that tree up there? Where that tree puts its next branch, Fibonacci. Okay? That branch is not random. It puts its next branch in the best possible place to get the most possible sunlight, and by Fibonacci. Okay? It blows your mind, man. It's awesome. At any rate, it's a cool and a novelist. Yeah, so many things. It'll blow your mind, really. But what's the rule? What's the pattern? There's a pattern. What is it? Adding the 2 previous numbers, okay? Now that's unfortunate because it makes it really hard to write a general rule. To know the 12th term, what do I need to know? The 10th and 11th. Now that's called recursion. When you need to build up to the term to get there, that's a recursive sequence. They're really unwieldy. They're hard to use because you have to build up to it. That doesn't allow you to jump to the 50th term, but it is what it is. In this case, the nth term would be, the sum of the one before it and the one before that. And so that's recursion. You can see that it doesn't depend on n. It doesn't allow you to just put it in and go like the rest of them do. It's recursive. Okay? Does that make sense? That is, one more thing. Can I throw one more thing at you? Sure. Okay, so I was going to talk some calculus. You can use calculus knowledge in here. Say I didn't say 4, 9, 16, 25 because I was just pretty much slapping you in the face with these are squares. But if I told you 10, 16, let's go with 5, 10, 17, 26. You might not have looked at that as, those are squares, plus 1. Okay? Nobody's going to see that, or not many people see that. But if you look at the differences, check this out. If you look at the differences, 5, 7, 9, and so on, the differences are linear. Now, if the differences are linear, then the derivative is linear, which means the original was squares. Okay, and you then just figure out, all right, what kind of squares? You can use that calculus knowledge, and it's pretty sweet, I gotta tell you. All right, let's go to the questions on the old fun sheet. We might not get through it all. In fact, we won't get through it all, but we'll get through it. All righty, here we go. How did the fun sheet go? Fun sheet, fun sheet. First of all, there was a fun sheet. Zoe Howard, turn yourself in the light. Scratch out. Gosh.
So negative.
Yeah, so negative. Okay. Number one, I know obviously I didn't put the proof there, but I feel like if you have a delta of epsilon over 7, you must be doing something right. You must know your stuff. Do you have that?
No.
Oh, proof. Okay. Well then, I was hoping I would get a whole course of, yeah, that's right.
I do.
Okay, thank you. Yes? Okay, I got a couple. That's good. How's linear delta epsilon going? Tell me that's going.
Yes, okay.
Now, I know this had a negative slope, and that is a little harder, but is it going okay linear?
Well, even if it's negative, I can just split it.
Yeah, you just have to call it, yeah, that's fine. And how about 3? Did you get delta is epsilon? Yes, no, okay. All right then. We will maybe go over those in more detail tomorrow, but let's go on to the, oops, these are definitely out of order. Let's see, is this? Nope. Here, let's just go this. Boom. Is this next? Okay, cool. So check your slope fields. You should have 2 zero slopes. Where are they?
-1, 2.
Origin and -1, 2. Now that makes sense because this would equal 0 if y is -2x. So I would have 0 slopes along that kind of trend line, yeah? What kind of slopes over here? Maybe here you're going to get flat and then more and more positive as x gets bigger. And here, these are positive, bigger, steeper, and steeper, 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 like that. And this one is a negative slope over here, and negative but not as steep slope. Yeah? Okay, when you drew the curve, here's the point that you're going to start from. When I go this way, eventually I'm going to come to the place where this starts to flatten out. So what do I have to do eventually? I have to go flat at some point, yeah? And then what happens over here? Ah, shucks. Now the question is, what does it do over there? We'll go to this finish point over tomorrow. If you are really lost on this, come 7:30.
Grace Thompson is
Because it should be
the
way out there.
Grace Thompson.
Have a great day. Yes. What in the world? Oh, yeah, that's fine. I know it's required to.
Yeah, and because
I signed up here, I'm now talking about the teacher, I should be back before stuff starts.
Oh, that's supposed to, no, it's not due today. We are caught up for one moment.